Topic 7, electricity in the home. The power grid is huge, and it's a very complex web connecting every building and home to the power plant. A power plant is where we have our generator. It produces a huge amount of electricity and then uses a transformer to convert it into a very high voltage. So, for instance, the generator produces electricity, and the step-up transformer will turn it up into the hundreds of thousands. So let's say 500,000 volts. This may have been like 20 or 30,000 volts. Steps it up and then transports it across the province or from wherever the generator station is towards a city. Once it's in the city, it's going to go to a substation and it'll step it down. And outside our houses, we often have a transformer box as well. So it moves through the lines from the substations to our houses and buildings at a higher voltage than what it would be to step down into our houses as well. All right, so we step it up once to move it across the province, and then we step it down a couple of times to use it in our houses. So the power line, so near your home, transformer lowers the voltage to a safe level. A small transformer for a neighborhood often looks like a metal cylinder on a telephone pole or a large metal box near the street. Electricity is transported at high voltages, so again 500 kilovolts or 500,000 volts, because it's more efficient and less energy is lost. However, our homes only use 120. They also use 220, so there is a little bit higher. The power meter outside our house reads the power consumption. The electrical power enters a meter on the side of your house where electrical usage is recorded, and that's how they track it to tell you how much you have to pay every month. The panel, so once it's gone through the meter, power is then routed into the panel, which is typically in the basement. The main circuit breaker shuts off all power to the house at once, just in case of an overload. The individual circuit breakers in this panel control the branch circuits located throughout the house. So like your dishwasher or all of the outlets in one room, the lights in a room, etc. We could turn off just that circuit if we wanted as well. Each branch circuit is connected in parallel to wall plugs, lights, and wall switches within a particular area of the house. And then those go, we plug in our appliances and lights. Normal housing wire in Canada usually contains 3 wires. The black is a hot wire. It supplies the current. The white is a neutral current, and it goes back to the source in that wire. So current electrons are moving this way in the black wire and this way in the white wire. There's also a ground wire. It's just copper. Sometimes it's green. It carries electricity back to the ground if there's a problem with your wiring. So rather than building up charge or maybe you have a power surge, the ground wire will take care of that and just reroute it back to earth. Older homes may not contain ground wires, so depending on the age of your house, you may not actually have a ground wire for all of your circuits. There is another type of wire sometimes, and it's red. And it also brings current, okay? However, it brings 220 volts usually, and this one is 120 volts, which we use in most of our appliances. Things like a stove or a dryer, these are gonna have the 220 volt. All homes must be wired to the electrical code. Only a licensed electrician is allowed to wire a home or a building, or you must have your housing wiring checked by a licensed electrician if you did it yourself. So homeowners can do it, but they have to pull a permit and then have it inspected. So there's a bunch of different safety features in our houses just in case. So in case of a short circuit, you are protected by circuit breaker trips, fuse blows, and a GFCI. So a short circuit meaning the electricity does not follow the general path of the regular circuit. So maybe you become part of the circuit, or something gets stuck into a plug. Those are the kinds of things that we're talking about here. So circuit breakers, so in our panel, the circuit will turn off. Sorry, that's not the one that's off. This one has been tripped. You can see here, often if something has tripped within your house and the circuit breaker has gone, you can see that all the switches are aligned to an on position, and then this one usually has moved out of position. So you can just flip it back on, and hopefully that'll turn everything back on. Fuses, if you have a fuse box, we have fuse boxes in our cars. So we can look there if something's not working in our car that was electrical and replace the fuse. GFCIs are a ground fault circuit interrupter. This is for water specifically, and so we'll find them in our bathrooms and kitchens of newer homes, and it instantaneously stops the flow of current at the plug itself if ever there was a short circuit. In our digital devices, there's also some microcircuits. There are conductors that are very thin traces of copper instead of wires. The resistors and lamps are quite similar to what we would have in a regular circuit. Transistors, or electronic digital switches, use a binary code for on and off. These are controlled by electronic signals, and then they can control other signals. Transistors are used in a lot of instrumentation. So, like within a building operator, you can turn things on and off, and those are usually done through transistors and a computer program. So when you're thinking about that, that's more computer programming to control electricity flow within a situation. All right, let's take a look at power here. So power is the amount of electric energy that is converted into other forms of energy every second. Okay? Or it can be the amount of energy that is transferred from one place to another in a certain amount of time. So converted from one form to another, or transferred from one place to another in a certain amount of time. So we see here that power is equal to the energy that is either converted or transferred over time, divided by time. So energy is measured in joules. Time is measured in seconds, which is important to note here. And power is in watts. However, we don't often actually measure electric energy. It's much more common to measure the voltage and the current and calculate power that way. So power is equal to current times voltage. Using these two formulas, we can calculate power in a variety of situations, and we just need to know which variables we were given. Were we given energy and time, or were we given current and voltage? So a current of 13.6 amps passes through an electric baseboard heater when it is connected to a 110 volt wall outlet. What is the power output of the heater? So to decide what formula to use, we need to list what we were given. We were given the current. We were also given the voltage. Therefore, from our two formulas, I know that I would like to use this formula because I have the current and the voltage when I'm looking for power. I do not have energy or time. So that formula is not helpful to me. So power is equal to current times voltage. So 13.6 amps times 110 volts. I get an answer of 1,496. And remember, the measurement of power is watts. All right, a dryer uses 4,500 watts of power and 240 volts. How much current is used? So I know that power is equal to 4,500 watts and voltage is equal to 240 volts. Therefore, again, looking at our formulas, I know that I need to use this formula to find the current, because current doesn't even appear in this formula. All right, we need to rearrange our formula for current. To do that, I'm going to divide both sides by voltage. So current is equal to power divided by voltage. Subbing in what I know, 4,500 watts divided by 240 volts, I get 18.75. Remember, this will be amps. Norman puts up his Christmas lights, which use 200 watts of power, and he leaves them on for 40 hours. How much energy does Norman use? So power is equal to 200 watts, and time is equal to 40 hours. We are now looking for energy. I know I need to use this formula, likely just rearranged to solve for energy because I have power and time. Remember, time must be in seconds. So I need to convert hours to seconds by multiplying by 60 twice, because I know that there are 60 minutes in 1 hour, and I know that there are 60 seconds in 1 minute. We get 144,000 seconds. All right, to rearrange our formula for energy, energy is equal to power times time. So 200 watts times 144,000 seconds is equal to 288 joules. All right, so this number looks like 28,800,000. Large number. If a refrigerator requires 700 watts of power, so power equals 700 watts to function, how many kilowatt hours of power will it require in a 30-day period? So energy can also be calculated in kilowatt hours instead of joules. To get this, we need to multiply our power, specifically in kilowatts, by time, specifically in hours. So let's just take a look at this. So our time was 30 days. So let's convert power into kilowatts. 1 kilowatt is 1,000 watts. So to go from watts to kilowatts, we divide by 1,000. And from kilowatts to watts, we multiply by 1,000. All right, so we're dividing by 1,000 here, and we get 0.700 kilowatts. To go from days to hours, I need to multiply by 24 hours in 1 day. And that's going to give me 720 hours. So to calculate energy in kilowatt hours, we're going to multiply our power in kilowatts, 0.700 kilowatts, by time in hours. I get 504 kilowatt hours. Ta-da! The cost of electricity, what we do is we take the energy in kilowatt hours and multiply it by the price of electricity per kilowatt hour. So in Calgary, the variable rate at this point was 6.777 cents per 1 kilowatt hour. So what is the cost of electricity for the fridge in the previous example? Well, in the previous example, we had that energy was equal to 504 kilowatt hours. So we need to multiply that number. So the cost is equal to the energy in kilowatt hours, 504 kilowatt hours, times this price. So 6.777 cents per kilowatt hour times 6.777. And I get 3,415.608, and that is in cents. So let's convert that to dollars by dividing by 100. That would be 34 point, and I'm going to round because we don't have that many decimals for our dollars. I'm going to round this to 34.16. So it's going to cost us $34.16 to run that fridge for 30 days. All appliances use different amounts of energy. Each appliance will have a different power rating, and the power rating tells you the rate at which the appliance will use energy. The EnerGuide label tells you very quickly how this appliance you're considering compares with other makes and models. So if ever you've been at Home Depot, this sticker should be pretty prominent in their appliance section. There's a few different things to note. So the annual energy consumption of the appliance in kilowatt hours is listed here. Okay, average. The lower the number, the better, right? We want to use less energy per year. The energy consumption indicator here shows you where this model compares to others in its class. So something in the same class might use 564 kilowatt hours per year, where something maybe at the higher end of the energy consumption, 972. So this one's like fairly low. Okay. The further this indicator is to the left, the lower energy consumption it is per year, and probably the better choice it is. The higher up it is less energy efficient in comparison to other models. And then they tell you kind of like a comparison value depending on what you're looking at, etc. So this would be different for fridges versus stoves because we're looking at different models. Efficiency. No device is able to convert energy with 100% efficiency. But the more efficient a device, the less wasted energy there is and the less costly because we are transferring energy more efficient. We're not losing as much that we're still paying for. Energy is often wasted as heat or sound. The efficiency equation is the amount of useful energy divided by the total energy put in times 100. So this is what we get out of an appliance, or also known as our output sometimes. And this is what we have put into our appliance, again, our input. Light bulbs are something that we talk about efficiency quite a bit. So light bulbs are designed to produce light, but are actually quite inefficient because they also produce heat. An incandescent, so your old school light bulb that heats up quite hot, is only 5% efficient. So 5% of the electricity that is given to that light bulb is actually turned into light. Halogen turns 15% of the electricity delivered to it into light, and a fluorescent is 20% efficient. So we can see that lights are actually very inefficient. So a light bulb receives 200 joules of energy, but only produces 10 joules of light energy. What is the efficiency of the light bulb? So this is the energy put in. So it's our input energy. And 10% is what that light bulb has as an energy output. So efficiency is equal to the output over the input times 100% to turn it into a percentage. All right, 10 joules was our output over 200 joules times 100%. In the end, that looks like 5% efficiency. What you should know is that efficiency is always less than 100%. So if you get a number that's over 100%, you know you've put your numbers into our formula incorrectly. Okay, so double check the question if you ever get an answer greater than 100%. Electrical safety is something that we have to talk about in this topic and just address really quickly. So a lightning strike can have 30,000 amps, more than enough to kill you. So to avoid being the target of a lightning strike, stay low to the ground, away from trees, and just generally be inside if you can during a lightning storm. Water, never mix water with appliance that is plugged in, like if you are cleaning something, unplug it. Don't handle electrical devices if you are wet or near water, and do not operate electrical equipment outdoors in wet conditions or in the rain. Don't put yourself in a place where you could be the pathway for an electrical current, so exposed wires, etc. Check before you dig. That's a really big one. It is a free service. So if ever you are going to dig a hole alongside your house where potentially there is electrical wiring coming into your house, it's really important that you have the utility guys come out and mark that. So the reason is you could end up digging into electrical cables or wires. And when you do that, you short circuit it and the current will come through whatever you are digging with, potentially into you, depending on what you are digging with. So very important not to hit those wires. Always unplug something before disassembling it. Don't bypass safety precautions when you're in a hurry. Don't put anything obviously into an electrical outlet except a plug. Don't overload a circuit by trying to operate too many devices at once or using one of those plug power bars that like a power bar into a power bar into a power bar is probably a bad idea. Cords, pull on the plug, not the wire. Don't remove the third prong. That is the ground on a third prong. Never use ungrounded or frayed two-prong electrical cords outdoors because they do not have a ground. And don't use devices that have a frayed or exposed power cord. Some practice here in the learning guide and then in your textbook if you're looking for something extra.